Hi all together. Yeah. Today we will go ahead with the PSO in the context of the simulation, MATLAB, better to say, MATLAB code. So we will repeat the concepts and we learn also a little bit some basic aspects or elements, I would like to say, of programming a little bit. But again, here is not a course related to, we cannot learn in a few hours, let me say, to be able to realize really program and so on. But I already uploaded and working and running, I would like to say, and working software, let me say so. And then in any case, after clarification, it could be possible, I think, that you are able to manage this software. Yeah, let me open MATLAB and let me restart shortly from the software which we considered last time, the program, which is in a program which came, I don't know if you remember, MATLAB, yeah, which came from my period in ABB, Eisen Brown Boveri. Of course, I modified, I simplified, I did a lot of changes in order to, yeah, uh, to be accessible to you in this sense. I mean, in ABB, I worked a lot on PSO, but of course, was inside these programs were inside and very complex, let me say, software. For instance, we used PSO to optimize or to set up coefficients of neural networks. In many optimization problems, we used PSO with different variations. We will see. It could be that next week, before starting with another topic, I will show you a possible variation. Also today, I will tell you without showing yeah, different variations depending on the problem which we have. Of course, variations are more suitable is relative to concrete projects. But anyway, I will tell you something concerning possible variation which can help to find optima. Okay, let me share. Nevertheless, PSO is a method, optimization method, very used in engineering at least, very powerful, extremely powerful. Now, the example which I am considering, you can find in my study 2 files at this moment. I will upload also other files today, and I think also at the beginning of next week, I will tell you a little bit again, but very shortly, and then we will start next week with recursively square. Recursively square is also important because could be a nice introduction to the topic model predictive control, because as you know, I came from the fields of control. Of course, the optimization, which I know, is not an optimization for, let me say, mathematical optimization, but is an optimization for engineers, I would like to say. This means more applied optimization. And one of the most important chapter, I would like to say, or topic in engineer is the model predictive control, which is an optimal control technique. And again, next semester, the upcoming semester, I will hold a lecture, a course in the sense related to the Kalman filter, which is another optimization method to estimate elements, its constant parameters, variables, state variable of a system. Okay, again here, you can find two files in my study at this moment. And one is with the name, we can see here, main program. And the other one is output function. Of course, originally we can see also here the software was inside in a complex structure. We can see here. I realized this in ABB Research Center. How possible to say? As I told you last time, with this project, including also PSO, but we didn't realize the pattern of PSO because we cannot realize pattern just in software. But anyway, just to emphasize that this method really can be used also in real applications. Yeah, the other file is output function, is the function to be optimized. And originally, everything was in one file. But I split because I think didactically is more, in my opinion, is more useful to consider two files instead of one. Please pay attention. This is the function to be optimized. Of course, it's an artificial function. In particular, the problem is stupid. Why the problem is stupid? It's stupid. It's not stupid, excuse me. The problem is, I would like to say the PSO is not suitable for this kind of problem. The reason is the problem so formulated, in particular, if you look at the cost function, we can see that this cost function consists of just one minimum at the point x1 equal 2 and x2 equal 3. We can consider also a different, we can extend, you can see here, also this cost function considering more than two variables, but let me remain so, because so we can compare, I don't know if you remember, with our example, which I put at the beginning in order to start didactically, with two variables to be optimized. No? So we can also figure out what happens here. I don't know if you remember in math. This structure here is in a paraboloid, and I can graph this function here. X parenthesis 1 parenthesis, X parenthesis 2 parenthesis is the variable, is the vector, let me say, with two components, and they represent our two variables to be optimized. We can realize that the optimum is it's always positive, is a convex function. The optimum is x1 equal 2, x2 equal 3, and its values is 100. I don't know if you remember. Let me draw or let me graph in order to understand why the problem is not, or better to say, PSO is not suitable for this kind of problem. We will see PSO will solve the problem, but it's not suitable because the problem is convex. X1, let me say here, X1, X2, X1 was 2, X3, X1, X2 was 3. And the value of this cost function, which looks like something like that, here you can find, we call here cost objective function, but Z, it doesn't matter, objective function. And this value is 100, for instance. Now, of course, the scale is different between Z and, yeah, is objective function. Yeah. Yeah. Nevertheless, I am considering this kind of function because at least we know the results, and then we can discuss what happens increasing the number of particles. We can discuss what happens reducing them. We can do many considerations because we can validate our considerations. I mean, the concept of validation is extremely important in in simulations. Extremely important because we can validate something, we can discuss about what we are doing if we know the results. Now, we know the results in optimization. Just if I consider an optimization problem, which should be, I would like to say, convex. Because if the problem is convex, we know when minimum, in this case, we know where the minimum is. We can see here x1 equal 2, x2 equal 3, and then we can do some consideration because we know the results. This means validation. Of course, if I am considering, at the end we will see a non-convex optimization problem, we will see very, very important this concept, that the program does not change. The problem is almost the same. But if the problem is the same, but if the problem is not convex, we don't know where the result is. This means we cannot do any consideration increasing a little bit. Yes, of course, we can guess what happens increasing or reducing particle or I don't know what. I know what, but at this moment I don't want to tell. But of course, we are in the field of hypothesis. Here we will see now that changing some parameters, some elements, in particular the number of particles, but of course we can change a lot of things. We can realize or we can validate or we can consider with more clear, let me say, concept, what happens. Please pay attention. I can consider again other variables, no? But why I considered now just two variables in order to figure out what happens. Because with two variables, I can graph. With more than two variables, I cannot graph. Now, of course, the dimension of the problem, this means how many variables I have, x1, x2, x3, x4, it depends on the problem which I have. Theoretically, infinite. But okay, theoretically, no? Or let me say arbitrary number of parameters. This is a function we can see here. This means it's not the main program. I don't know if you know some knowledge in informatics, let me say informatics, in programming, better to say. The function must be called by another program, which basically we call main program. Okay, let me go ahead. Tick. This means we have a talk somewhere in order to calculate the time between the line 8 and another line. We close this let me say, this loop or this part of the program in order to have an idea about the calculation time. Typically, the calculation time is not exactly in a parameter which is said as an indicator, of course, can be used, but it's a relative indicator. Why is it a relative indicator? It's a relative indicator because the time of execution depends on the microcontroller which you have. Depends on many things, the tool which you have, the computer, everything. Let me roughly speak it. Very important are, I would like to say, the calculation law, the number of operations which I have to do with the program. But in any case, it's as a relative indicator is very, very often used. In the sense, we can nevertheless calculate between tick and tock. We can have a good idea if I introduce in a method variations. What is the cost? Can be done before the variation and after the variation between tick and tock. I show you later. The computer will print the running time between tick and tock. CLC, do you remember? If I remember, CLC clear the command window. This basically is relevant. Clear the variable which we have here in the workspace. Close all closes the figures. Format long is a way to represent the variable, the results with the maximal number of decimals, but it's just a representation. The precision, if you want to increase the precision, you remember last time I told you if I remember well, is something like that. I don't remember. You have to look here in relation to digits. Yeah, look here. If you want to increment, the precision of the machines, use this one. Here is just a representation. RNG default is yeah, we have with this, we have the possibility to use different random number. Here, default is in a uniform distribution between 0 and 1. This is the standard, let me say, therefore default way to generate random number. Do you remember the random number is extremely important in this context because the PSO as the genetic algorithm is based on the randomization of the, let me say, distribution of the particle. Of course, we can use different distribution. We can use also chaotic distribution and so on. But this could be a possible topic in our project. Line 15 is basically in a line which states a vector. We will see, we will use at the end. Without dimension. I mean, theoretically, I put here a number, let me say, unlimited of elements. Unlimited means until the overflow of the machines. Without dimension, this is. LB and UB. Do you remember the concept of LB and UB? The concept here is related to the field, let me say, the search space in which I will assume that the minimum is of the optimum in general. I mean, here I am assuming that the minimum is between -3 and 3 and between -9 and 10. This means x1, which minimizes the function, I assume that is between -10 and 3, and x2 is between -9 and 10. It is a good hypothesis in our problem because you remember x1 was 2 and x3 was 3, I remember. This means here inside. Now we will see what happens if my assumption is wrong in the sense the minimum is not inside this interval. Yeah, I mean, if you want to understand exactly this representation, this boundary, let me say, basically, so now I already forgot. Let me see. LB is -10 for x1 and UB is 3. Let me see here, -10 for x1 and here is 3. This means x1, I will search randomly here. X3 is -9, 10. X2 is -9. Let me see here, 10. Of course, this is a little bit strange, the scale. This means I will look, I don't know if you can understand, the search space. I will look on this region here, characterized by this rectangular region. I will look here in this domain, let me say so, in order to use the wording which you know, the minimum. The minimum is here. And we will see that the PSO will try to find this one. Of course, again, to solve this kind of problem, it's not necessary PSO, it's not suitable PSO. We have also method like Rapson-Newton, this tangent method, more efficient. More efficient means for this kind of problem because we have a less number of calculations, less running time. But of course, in this case, it's also stupid because if I know that the cost function, I can calculate analytically without numerical approximations. But anyway, we will see how important, nevertheless, this example in order to understand the method. Now, again, we can understand also from this representation why I am considering just x1 and x2. In this case, I can explain very well this research area, the search, no? The search area or the search domain, you can call as you want. Let me now come back on the software. Of course, I have to know where more or less is. If I don't know, I can write, of course, here minus infinite plus infinite. But in this case, of course, if I put here minus infinite plus infinite, the algorithm, it could be that it needs a lot of time to search, because plus infinite, so theoretically, is large LB in absolute value, large UB, means that it could be that I'm not able to find in a microsecond the minimum, or a value which is nevertheless acceptable for us. Of course, there is the idea is, if you look in the literature, the effectiveness of the algorithm depends also on, let me say, the density of the particle, and the density of the particle is related to the number of the particle with respect to the dimension of the search space. Again, do you remember last time, this to be the example, as I told you, if I ever do search in this room alone, the key of my key is not the same thing if you help me to look in the same area together with 3 or 4 people. Here it's easy to understand. If I have 1 million of particles instead of 1, of course, the probability that let me say, the algorithm will I mean, in a convex problem is not so extremely important. Nevertheless, the probability that I will have some very quickly some particle in this region is higher than if I have just one particle, because one particle have to move over the steps. This means over times to this one. This means the density, the number of particles divided. Let me say the dimensions, in the sense easy to understand, the surface which represent our search area or search region is the element which must be taken into consideration. Must be taken into consideration. 1 second, let me share again. This means LB and UB are extremely important. We will see later what happens if the minimum is outside, no? Because this is an hypothesis. The dimension is 2 variables. I assume 10 particles. Do you remember V max, V min is the maximum and minimum value of W. Here is fixed. Of course, this could be also variable, but let me fix. Then we will see. C2 and C1 I fix equal to. The reason is could be also variable. This could be also adaptive over steps, over time. Step equals time in our case. Is equals to, because if R1 and R2, I don't know if you remember that, I will come back on this, the structure of the PSO, are random variables, uniform distribute between 0 and 1. This means the mean value is 0,5. If you want to weight, you remember the component B best, the component G best with the same weight, statistically you have to consider the factor 2. But this also could be an interesting variation. We realize the different variations considering C1 and C2. This dynamic acceleration factor, I told you about this meta-heuristic acceleration, could be also considered which change over time. At this moment, forget this intermediate iteration also is important in case of some variations. We are just considering maximal iteration to start. For project, we will see that we can consider also, and now I will clarify what we can use this here. Maximal loops. Also here, to think about one, basically don't consider this, but believe me, it's easy to understand that I can use for different tasks more than one swarm, let me say parallelly. I will try probably next week very shortly to tell you about this possible variation. At this moment, we have just one swarm. just one swarm. Also here, everything related to Max-Run loops, forget, because otherwise too complex. Also this one. Also here, this 4 here, you can forget because it's related to maximal loops. We have just one swarm. This means this loop here is not active. Exactly. Here we can cancel this. Yeah, just to it was here because run is basically our index for the loop, which start in 47. But as I told you, basically we don't have this loop because it's running just one. No? Then very interesting here, we have the loop which start with 4i and 4j, and we will close with end and end. The for loop means I fix I equal 1, and I will run j from 1 to m, the command which is here inside. Again, at the beginning for I equal 1, I will run j from 1 to m, then I will increase excuse me, and I will run again j from 1 to m. What is the meaning of this? The meaning of this that I fill up an initial position, we will see, of my swarm, considering randomly variable between LB and UB. Why that? We can see from here. No? This is not the unique way to do. We can see also another way, possible in other ways. But the reason here is because of these random variables is the variable between 0 and 1. When the random is 0, almost 0, we are on LB or almost in LB. When random is 1, we are in UB. I don't know if you can see. This means that each let me say loop for j, because j, let me say, depend of I, if you want. No, for each I, we have a full loop of j. I will obtain my search area, or better to say, I will fix randomly I and j, I will fix the particle in my search area. At the end of these two loops, I have randomly, where is it? Until here, no? Until here. I am randomly the position of the initial, let me say, I have randomly the initial position of this wall, this here, x0. It's nematic, x0 nematic. Randomly, calculated, let me say, inside LB and UP. I change just the variable. I fix the initial value of the velocity. Do you remember? We have position and velocity. And then here, very easy just to understand. What I'm doing here, I know the for loop, but this time just for, let me say, each particle. What I do here, I call my output function. Do you remember this paraboloid in 2 dimensions? And what I do with this command, I calculate my paraboloid in my, let me say, domain. For each, this is the way to represent every j, for each j, or let me say, in all domain. I will switch on the lateral camera to understand better this one. You can see this. For I equal 1, I will call the function, and I will calculate the value of the function for the particle 1, considering all its coordinate, its coordinate, I would like to say, both. And I save is a vector. Why is it a vector? Because to characterize a matrix, I need I and J, but here J I don't have. This means I will calculate the function and I put the value which I obtain in a row, one row characterized by the index I. I show you what I intend. What I am doing with this operation. For the particle 1, I have its coordinate, which came from the randomization, for instance, this, and I don't know this. And then I will calculate, calling the output function, its value. And I save this level here, which I don't know, could be 200, I don't know what, is in a vector, in a row vector, characterized by the index I. Like I use the index as I want in different contexts. What I intend with this sentence. This is the index of the vector F0. It's a vector because we have a fixed this dimension, the second dimension, 2, 1. Really, I make mistake. It's in a column. F0 is in a column. It doesn't matter. Anyway, it's in a vector. A column vector. Because I represent the row. Okay, now I will calculate the minimum once I calculate the position. The value of the particle, let me say for each particle, I have a vector with length equal n. And then I will calculate the minimum, this is a function of MATLAB, of this vector, what is the minimum, and I can save the value of the minimum in the first element of this vector and its position. Its position means I localize what is the particle which have the minimum and what is the value of this minimum. This is basically it's a vector with two components. I put x0 equal p best. In G best, I will put the best particle. We can see x0 is the position of the swarm. The swarm at the beginning, we are not flying, not yet. We are in the initialization phase. Do you remember the last time I clarified this? And I put in G best what? The best. Basically, this is one particle characterized by, I know what it is. Could be the first, could be the second. And all its coordinates. Better to say its coordinates. In our case, we have in a row with two columns. The best particle is characterized by x1 and x2. Now in the initialization phase. Why that? Because now we will start to fly, let me say to fly, in which I fix the number, an indicator reflect in the number of iteration. About the tolerance, forget now, but you can understand that we can check an intermediate. You remember this word, intermediate step in order to see, we will see later better, in order to see if it's worthwhile to go ahead with the software, no? Because sometimes it's really heavy, the calculation low, the running time and so on. I will come back on this later. At this moment, forget, otherwise too many information, but try to guess that I can check, we can see directly here, no? If some tolerances are satisfied and so on. Now we will try to fly. Fly means while is in a cycle like 4, let me say so roughly speaking, in which the iteration we will update at the end plays an important role because until iteration less or equal to the maximal iteration, I will run everything inside the loop characterized by while. While will finish with an end. It's quite similar to for. No? Here again, as I told you last time, we have the weights of the previous velocity. We can see that I am considering here a variable weight between Vmax and Vmin as a function of the iteration. We will see this iteration will change. First iteration, second iteration, I will increase this counter. Until maximal iteration. We can see that for iteration very, very small, theoretically 0, we have that we are Vmin. We can see, excuse me, Vmax. And if iteration equal maxima iteration, we have a Vmin. This means we reduce the contribution of V, the old velocity, over time of the overstep. The reason is we try to converge in one point. This means we trust the work of the swarm in order to emphasize the exploitation phase over time. But about this we can discuss. What's in a typical. Now, these two loops. The first loop is the loop for the velocity. I don't know if you remember. The concept is a little bit complex because remember we have here. Let me move 3 vectors. This is the old velocity. Here we have a random vector because of the random variable here, which updates the velocity considering the position, the preview position of the best population. I will clarify this a little bit later, but you remember last time I theoretically told you this is the matrix in which I put when I find the best element, but consider the population, not just the best of the best. When I see that an element and a particle, the step in which I am considering the program is better than the before, I will replace. Yeah, it's the best population, the best swarm, which I intend, now we will see later a little bit better, when I have the best bird, I will replace in this P best. And then I do the difference with the old one. We can see later what I intend. Here is more interesting this, because here, do you remember, I will orient, let me say the old position, considering just the best. Because G best, if you remember, is in this case in a row. Yeah, the comment is a little bit strange. Is, let me say, wrong, because we have I reduced the dimension to 2. No? But in the next example, I will increase to 3. Therefore, remained 3, even though in this case here is 2. No? Is in a row with 2 elements in this example. And later I will show you with increasing the dimension, and then I have to put 3. But I forgot to correct. Now it's correct. Exactly. In G best 1, J, we have the best element. And MATLAB understand that each row, let me see here. No? This is an row with 2 elements in our case, but could be 3, could be 4, depending of the cost function. MATLAB understands that each row of this, because of J, which is running the coordinate, must be recalculated in this form. This means somehow we reorient the previous swarm, or the position of the swarm, considering the best, the position, when I say the position, I indicate J, no? Because J is from 1 to 2, indicates the coordinate. Consider the position of the best swarm. I can show you a little bit later. Okay, and then I update the position, considering the velocity. And then look now, interesting, I will check here with this 2-4 loop if we are in the boundary or not. If we are in the boundary, I put the boundary. Basically, if X is outside the boundary, this means or yeah, in the sense is outside, I put the boundary because I am searching just between LB and UB. This is for LB and UB. Now, the problem is here, if I am on the boundary, this means I don't have the minimum, or better to say the relative minimum. This means that we have to reset the boundary. We can do something also different, but I will tell you probably next week. Then I call again the output function, and I will calculate the output function for the new position. This is the new position, X. Could be on the boundary, but we hope that is inside. Because on the boundary, not a valid minimum in the sense is the minimum of the interval, but we're looking for a relative minimum, which hopefully is the global minimum. I calculate, I put also again in a column. And then very important is for loop from here to here with inside an if loop. What I'm doing here, I ask if, no, let me say I ask, if the new position, which of the new value of the function calculated the new position of the swarm is less than the old one. Think about F0 as the initialization minimum. If yes, this is the sense of the if, no? If yes, we do this operation and this one. If not, you don't do anything. You don't do anything. This is the sense of the if. It's a little bit more complex than 4. 4 is just running. Here is a little bit more complex, but what is the meaning of this? Basically, if I have something better at the step 1 with respect to the step 0 initialization, I will put what I am better, the I, which is better, with its coordinate, or all coordinates, if you like, in P best. Basically, I replace the position, the old position with the new one because it's better, no? In accordance if this if is positive, is yes. And very important, I put in F0 the new value. Why that? Because F0 at the beginning, at the step 1, is the initialization value of my first search in the initialization search. But then I will reuse F0 for the step 2, for the step 3. This means I have to replace what I have if it's the best, if it's the best, if it's better, let me say, if it's better. in the F0. So each time I will reuse F0. I calculate the minimum of F0 and its position, the minimum on F0 and its position. Yeah, forget it because run, which is an indicator of to use more than one loop, I didn't include now in this variation because I would like to explain the basic is already complex somehow. What I am doing now, I need to complete, I almost at the end. No? I need to complete the G-best, no? Because P-best is clear what I intend. Each element for the whole swarm, if a step 1 is better than the step 0, I will replace. At the step 2, I do the same. If the step 2 indicates that the new position of the swarm, the particular swarm, is better than before, I will replace. But for the whole swarm, here we are considering now the best of the best. Look, I will consider the best of the best because I will consider the population best, but consider just the best of the best. For all each coordinates, or consider its coordinate. And I put in G-best. Index indicates the best of the best, which I have for all population P. G-best, very often global best. I put also in this case the value of the best in F means 0 in order to be reused also. You remember F means 0 as F0, this was also present at the beginning in the in the initialization phase. We are almost at the end because now we have P-best and G-best. Forget this because again, everything related to the indicator N we didn't consider here. Tolerance also we didn't consider, but we can understand that we can complicate the algorithm introducing some checks in order to reduce the time of calculation. If it doesn't worthwhile to go ahead, I will clarify now a little bit better. Now I can print the results, which is in G-best, because G-best is what we want to attain, the best of the best value where we have the minimum or where we supposed to have the minimum. And then I can calculate for you. Instead of x1 and x2, I copy the same expression, but I put a G-best 1 and G-best 2. We have a G-best for x1 and G-best for x2. I increase the iteration. I will fill up my vector. Remember, this f-min plot we will see for the plot is the vector in which I accumulate each time the element of f-min plot. We can see on the left we have f-min plot, on the right f-min plot, but I will add the last minimum which I'm finding. I will clarify with the plot what is this vector here. At the beginning, do you remember we defined this f-min plot with infinite, let me say dimension. Infinite means anti the overflow. This end here conclude my while, and this end here conclude my run, but this is not active. It's there because I upload it for you. Sometimes if you decide to work on this PSO, could be nice, could be useful to consider in the project some different variation with tolerance, with more than one swarm. Anyway, this means it's there, but you remember run, the indicator 1 is 1. This means it's not active. Let me run. Change folder. I hope no mistake, because sometimes the student asked me some changes and then I forget to. As you remember, 100 is our minimum. Calculate it. Oh, the PSO find x1 equal 2, but not exactly 2, and x2 equal 3, but not exactly 3. No? The reason is it's numerical approximation. Not only connected with this numerical approximation, I have to say, you remember last time, if you consider, excuse me, the problem is just in one dimension in order to calculate or to live a little bit better in such kind of problem. If I consider just one dimension, you can do at home, reducing to one dimension. I show you if you want. I don't know, x equal x1 equal to. Just try to consider in a section of this paraboloid with just an intersection considering a plane orthogonal to x2 or something like that. Ideally is a function which looks like something like that, a parabola, remember. 100, and the parabola here is z equals x1 minus 2 square plus 100. But of course, in our numerical representation, it's not exactly so, but something like that. Because we have a numerical representation of this surface or this parabola. This means numerically the problem is not convex. It could be that I'm here, it could be that I'm here, and not exactly in two. This can be understood if I increase, for instance, the number of particles. If I increase the number of particles, the probability, but just in a probability that I am closer and closer to the values 2 is higher. This, you remember the concept which I explained before. The density. The density of the particle is extremely important inside LB and UB in order to find the solution. Now the solution is 2 in our case here. Or in the case which I am considering the software is 2, 3. And that is, of course, just a probability, because don't forget that the method, excuse me, the method is a random method. But let me see if I'm able to show you this concept here. Let me copy this. Of course, for this easy example, it could also not be valid, but typically yes. Now, what happens? The question is, what happens if I increase the number of particles? Theoretically or statistically, I will fall down in a solution closer and closer to 2 and 3. Let me see. But of course, statistically, if I go here, where is now? Yeah. Instead of 100, let me like 1000. Of course, I will increase the calculation time. I don't know if I copied here. Probably yes. Let me copy these two values. Let me see if I copied. Yeah, I copied. Okay, let me run. Not necessarily will obtain a better result, but statistically, yes. I don't know if we had. This is the new values. Let me compare with this. Here it seems to be better. Now let me see. 2, 4, 6, 8. 2, 4, 6, 8. No, with is not better. And also here it seems to be not better. But as I told you, is something statistic, probably increase more or decreasing with one should be worse than this one. But also this is something statistical. At this moment, we have this is the best with 10, which is the best with 10. Let me see with 1 what happens. Totally wrong. Oh, we can see. The reason is with 1, we will remain somewhere. Show you. This I clarify also wrong this. No? Let me. We will remain somewhere. Here, we can see here in one dimension, we will remain somewhere in one numerical local minimum. The system which I'm considering, the cost function, is mathematically convex. But of course, numerically, we have many valleys and many hills. But of course, one particle is a little bit strange because with one particle, we cannot speak about the swarm. G best is equal P best. Let me consider 2 elements. It's already more meaningful. The reason is that at least we have the swarm. We have the difference between G best and P best. With 2 elements should be definitively better. But of course, nevertheless, relative wrong. No? Increasing, we have better and better. It seems to be that we have a saturation, because you remember I put 1,000, 10,000, we didn't have an improvement. The reason is that, of course, we have this is something valid, but statistically, it could be that we have also an optimal. I read something about that, an optimal number of n. But this means this is a very interesting problem. I try to explain why this is interesting in this sense. Why we have an optimal number of particles. This could be another interesting project to optimize the number of particles. Assuming that to build my house alone, I need 1 here. If you help me to build my house, 2 person, I can assume if the system is linear, we need half here. If you consider 4 people, I can assume that we need just 3 months. But if I enroll 1,000 people, you can believe me, we'll never finish my house. What is the meaning of this? Also, this concept of P-best, with the indicator of the new direction, the indicator of what we have to do at the next step. Sometimes, if the swarm is too large, not necessarily we find the best indicators, the best indication to go ahead. No? The example of to build a house is interesting. Alone, I can consider to finish this work is 1 year with 2 people. I can consider half a year. 4 people, 3 months. But 1,000 people never finish the house. Just to understand that the problem is a little bit more complex, and n could be also, in the sense, the density could be also a parameter to be optimized. No? But anyway, I'm not expert on this, no? But I try to give you some interesting indications for possible projects. Okay, let me go ahead a little bit. Next week, nevertheless, before starting with another topic, we will come back on variation and so on. Let me consider just one dimension, and then I will show you in a real project, even though in a simplified form, in order to see how the program is exactly the same. This means this structure here is in a basic structure. We here in my lab we consider also variation with 2G-best with priority, without G-best. Depends of this optimization problem. Now I don't want to tell you much about that, but next week I will tell you net transformation of the search domain to improve also or to reduce the stagnation of the particles. Stagnation means when the particles remain too long or don't move from the region. Now, if the problem is convex, we can see that the most important thing is the number of particles. Again, we can see that we have a saturation. This means not necessarily an infinite number of particles is better than a finite one. We have seen also here, because in the problem of optimization, again, the stupid example to build my house is an important example. It's difficult to optimize the work of 1,000 people. I am sure that we will never fit the house. Let me now reduce the dimension, how easy to modify this, and then I will show you in a real project, and then we upload, which is basically the same like this. Okay, let me go in the out function. Let me now consider just this plus 100 semicolon this. You can see now the active function consists just of one dimension. This is a parabola. Exactly as a graph and with the lateral camera, let me say so. What I have to change here? A few things. M equal 1, number of variables. Now we don't have x1 and x2, we have just x1, the number of variables. Let me remain m equal to, but let me consider 10 or the 20. So we find more correctly the minimum. The rest, I have to change that just LB because UB, because now we don't have a rectangular search space, but we have just a line. Let me show you in. Now, if I'm reducing, we are considering just this. Between, I don't know what, but let me include the two. Like here, I am considering just this. No? Because I'm assuming that I am interested just in x1, just to show you something for you. How easy now is to... This means, let me say so. Between -3 and 3. What I have to change, basically, I don't have to change practically anything, but you remember at the end, in order to visualize the solution, I put it here, that's this calculation here. No? Now should be considered just one dimension. No? This means I think I didn't forget anything. But this, of course, is just to visualize the results. Right? If you want, you can cancel this. Let me run. I think no mistakes. This is the results. It's equal to, okay, I put this semicolon, therefore I didn't visualize the results. You remember I told you at the beginning, this semicolon here means don't print this line, this result. Well, we can see the result around 2. We didn't improve the precision. We can using this VPA. Look, 100, it is approximated. It's a little bit strange, this approximation. I cannot clarify why. It should be not 100. Should be something more. I don't know why. Probably depends of how is set the cut of calculation. I don't know. I cannot explain why. Should be something more than 100. Try to use VPA with digit, but it's not relevant for us because it's just to look. But of course, it's not 100 because 100 is at 2. We are not at 2. Very important now, before showing you in practical example, more practical example, which is basically the same. What happens if I set LB between -10 and 1? Interesting, because now we know that the minimum is a 2, but LB is okay, but UB is not. What I intend is this one. The interval which I am fixing, but in particular UB, excludes. Basically, I'm searching between what I told you, -10, something like that, and 1. But between -10 and 1, we don't have the minimum, because the minimum seems to be at 0.2. What I'm waiting for, that's the PSO will crash again this upper bound, because the PSO will remark, we see that the minimum is outside. Let me see. Because the PSO will surge in this region here, slowly, the particle, slowly, depends of how accelerated this. I didn't tell you about the possibility to accelerate the algorithms, but in any case, we will find this minimum here, which is the local minimum on the border, of course, of this interval here. Or if you want, is the global minimum considering the interval which I fixed. Let me show you. I am waiting for, instead of 2, 1. No? Or very close to 1. That's numerically, of course, we can have but I think it should be 1. No? Yeah, we can see here G best, which is our solution, is 1. The meaning is that PSO sees something better outside of the interval. If I increase again, we will find 2. I don't know if it's clear what I intend. If I put 3, I will find again 2. G best is our solution. Huh? Again 2. In the same way, if I put here 3 and 4, what I'm waiting now, I will find 3. I don't know if it's clear, because 2 is outside, but less than the lower part or the lower boundary. I mean, 2 is our minimum. If I fix 3, 4 as search space, I will end up here. 3. Let me show you, because the PSO try to go towards the minimum, but will crash, let me say, against the lower bound this time. And this is due to this check. This 2-4. No? Yeah, we will check if it's outside of the boundary, we fix the boundary. If what I'm looking for is outside of the lower bound, in this case, I fix the lower bound. Now we are waiting for 3. No? In fact, it's not 100, 110. 3. Fixed, because we fixed. We put exactly the boundary. I think I explained everything here. Let me open an real project very quickly. We will see how similar is, or we can do next week probably. It's better because nevertheless I need to clarify some aspect, but nevertheless we will see that the structure of the software is exactly the same. The problem which I would like to show you next week is an approximation of data which stay the roughness of an surface. Remember I told you at the beginning, you have to minimize using a robot, the roughness of an surface. The variable to be optimized is omega and v, rotational velocity of the end effector and its translational velocity. But of course, before considering this optimization problem, we have to consider another optimization problem, which we calculate the cost function, which is the roughness. And this is built within a fitting problem, which we have seen also the meaning of the fitting problem, considering at the beginning the least square method and so on. Now we will consider with PSO, why that? Because the problem is not convex. Not convex because the regressors is in a mixed regressor. In this case, which I am considering next week, is an exponential regressor with different exponentials. And this means the problem is not convex anymore, you know, because I cannot distinguish between what I have and what I don't have. Let me do next week this. I don't need much time, but it is better to, because it's a little bit in a different cost functions on, but the software is exactly the same because it's exactly the same. The cost function is built using exponential functions on. Or better to say the least square with the regressor of the exponential function, we calculate the parameter of the exponential functions, which characterize this new regressor. And then, of course, the step after that is to calculate the velocity of the robot. But this, I have also somewhere, but it's not necessary I have not necessary to show you. And then I will show you this way to manage the search space in order to avoid stagnation of the particle, in order to have a more effectiveness, let me say velocity, also in the sense position of the particle. The reason is the most important phase is the initialization phase or exploration phase, because if we have a wrong let me say direction at the beginning, sometimes it's difficult, but of course we can modify the algorithm as we want. But the most important thing to have the right direction, or the good direction, a suitable direction, starting from the beginning, and then sometimes to transform with the transformation with the function the search space could be useful. I will show you just one idea to get after showing you this practical, the real example, even though simplified for you to be understood better. Okay, let me stop here. I am here for questions next week. Nevertheless, I think I will dedicate 15 minutes, 20 minutes, and then we will start with a new topic. New topic is recursively square. After the recursively square, I think we can conclude the course just MPC, considering MPC, which is in control, optimization, optimized control strategy. If I have time, we will see something about Lagrange or Hamiltonian, but I don't know if I have time. Otherwise, we can consider in project. Of course, I will assist you on this rest of the topics, even though I will not able probably to go in depth or to tell you about that. But the concept of the optimization, I think we have seen during at the end, I hope. I am here for question.